Yeah, thank you very much. So a few words to myself. I work for Genua. We are a company building BSD-based, OpenBSD-based firewalls. And I'm an OpenBSD committer since 10 years now, so I can combine my profession with my hobby. So what we'll talk about, first of all, why do we need something else? It has been said already, Syslog is a very old program and just works. And that's what we expect from it. Where are we now? Starting position. What did I do to make the local logging better on the machine? What did I change with remote logging, sending Syslog messages to other machines? And I have a short summary of what I did. Oops. Yeah. Okay, why do we need logging and why do we need reliable logging? So we do system analysis. We want to know what on the machine is going on if we debug a problem. And if some log messages are missing and we don't see that, then it makes our task harder. Second thing is we have attackers in the internet, and they try to avoid that we see their traces. They try to avoid that we see log messages, so if they can bring the system to a state where it doesn't log anymore, they can make their attack and we don't see that it did something evil. And then the third thing is we certify. Yeah, we are on time. We do a certification for our product with common criteria, and there someone wrote into the documents, yeah, we do reliable syslog and we don't lose log messages. So we had a bunch of dirty hacks in our product to make that, and I thought, let's move all the intelligence into the system, into the syslog, so that the community can have an advantage for it, and we have cleaner code and don't require our hacks. So what can go wrong? First of all, Syslog is doing, if it does remote logging, it with UDP forever, and UDP is not known for being reliable. It's basically unreliable. You can just lose it. If you lose the UDP packet, you don't see the log message. Then we have Unix datagram sockets for local delivery. There you need file descriptors. Then you have to need access to the file. You can be run change rooted. Then you don't see it anymore. So it's def log. That's the classical thing. And there are things that can go wrong. And then we have timestamps and time zones. When you run change rooted, the classical syslog takes the time zone from the local file system and the client who is logging it. So when you forget to put your etc local time in your change root environments, you get syslog messages that are in different time zones. Some of them are UTC, some of them are local time. And timestamps is also a problem when you do remote logging, when you have a global environment, and every syslog is logging in local time, and then you have a common log file with all things, and every machine has a different timestamps. That's really hard to debug. Okay, where did we start from? So that's how syslog works when you just go through. So that's how syslog works when you are a C programmer. So there's a libc function that's called syslog. You can say, okay, I have several severities here. We have an error message. You can do some printf style formatting. Then everything goes to libc. There, the priority is processed, so this is converted to a number. You have timestamps that are added there. The print is done, and then it's sent to devlog. That's a Unix Unix domain socket, and the syslogd is listening on that. So then the syslogd is receiving the thing, writes it to a log file, or sends it via UDP. So this has been there for forever, more or less. So now we look into details, how that works. So we have some priorities, facilities, levels, severities, and options that we can pass. There, the first confusion starts. The man page speaks of level. The RFC calls it severity. The header files calls it priority, while the RFC means the combined thing between severity and facility is the priority. So what do you do? We have an open log. That's a libc function that a program calls when it starts running, and there it can say, okay, my name is FTP daemon, so tag this name to all the log messages so the user knows where it comes from. It can say, okay, and I want that my PID file, my PID number is logged in all messages, and if logging goes wrong, the message, so if cannot reach syslog, the messages should show up at the console. Then you can say logcons, and there are some other options there. And then we have the facility. Facility means that every program, that there are some classes of programs, for example, FTP programs. Then we have UUCP, the news, the syslog, the mail. So it's basically what a server in the beginning of the 80s could have. And then we have local facilities, local 0 to local 8. That's everything else. Or it's local 16, I don't know. So those are our numbers, and the facility and the severity, they are ORed together, and then they're called priority. And the libc generates such a string. So this one is in decimal notation, those two ORed together. Then you have the timestamp, that's the classical BSD timestamp. Then the program name, the PID, and the message. So what can we change here? So we write that to devlog. That means we need a file descriptor. So when do we acquire the file descriptor? We can either do it with OpenLog, or we can do it when we do the syslog call, and there we have a special switch, that's nDelay. When we say no delay to OpenLog, it opens the file descriptor immediately. So that has an advantage, so you have opened it at once, so before you change root. And also when you go into a change root environment, then logging still works, although you have no socket there. But then you get a stick up to the syslogd. That means he closes all the listening sockets, and you have to reconnect. libc will do that unless you're in change root, and unless you have specified syslogd to add an additional log socket into the change root. And then Theo de Raad added pledge to OpenBSD, where you can specify that only special classes of system calls are allowed. But you want to allow every program to write its log messages because they are the errors, they are the traces for the attacker, and that's common. So all this concept makes it quite complicated because you need this file descriptor, you can run out of file descriptors because you have this log nDelay, you have to reopen it during operation, you have to allow somehow syslog socket, somehow the Unix domain socket, so you have to pledge Unix everything. So that's not good, and when you say logcons, then the libc makes a send to, and sees, oh, syslogd is not running. Now I have to open the console file descriptor, dev console, so you need another device in your change root, don't forget that. And you need a file descriptor, so if you run out of file descriptor and want to log that, it doesn't work. And so that's the implementation nightmare, especially in situations where something went wrong. So what's the solution? We have a new system call. So Theo invented it, it's called send_syslog. And there we move tasks from libc to the kernel. So how does it work? It has an integer return value like most of our system calls. There we also see some error if something didn't work. For example, no buffs if you ran out of mbuffs. And you put in the message. It's not null terminated, or in most cases it is. But basically you give a length of the message, and you pass some flags. So there's only one flag supported at the moment, and that's logcons, where you have to want to log on the console if the send to the syslog fails. And the advantage is that you don't need a file descriptor, because the kernel has opened the console anyway, and it knows what to do. So it's not task of the program anymore to grab the console, the kernel does it. So here's an example of what I call. I put in the string, the length, and the flag. Yeah. No, does not. Okay. The question was whether I need the PID here or not, and I need it. All the other processing is still in libc. Kernel is only responsible for sending it. So libc will generate the priority, the timestamp, the name that you gave with OpenLog. Otherwise, you have to store all that in the kernel. It adds the PID. So the PID is not reliable. Everyone can send whatever PID he wants. And all the printf processing, it's still done in libc. So how do we get the message out of the kernel again? Before, syslog-d just opened a listen socket on the Unix domain socket. And here, syslog-d creates a socket pair. A socket pair is a system call, and you get, it's something like a pipe. It's a socket with two ends, and you can write in one end and get it from the other end and the other way around. And then syslog-d tells the kernel with an ioctl, it opens def klog and does this ioctl with a file descriptor of one end of the socket pair and says, oh, this is my logging file descriptor. And then the kernel registers it, and it knows one logging file descriptor, and every time you call send syslog, it uses this. And syslog-d listens on the other end. And kernel writes into this socket pair because it knows which one it is because of this ioctl. The kernel also knows when the send-to doesn't work, then it writes to the console. It has it open anyway. You can ktrace everything that's going through there. We have added some ktrace hooks. Just have to ktrace the program, and you see what it's logging. Normally, you write a file descriptor. Here, -1 is written because the program doesn't have a file descriptor for that. And what is new, I can count the errors. The kernel can count the errors. So what does reliable logging mean? So either when we see, oh, we cannot log anymore, we hold the system until it works, but we don't want that. And so my solution for reliable logging is counting the errors and log the errors when it works again. So you see there was a problem, the system works and continues, and then we say, and be careful, we lost 5 messages. And here, the kernel can count the error. We have one kernel, one central place, and every time the sending to the syslog-d fails, it increments the counter. So we have it on this slide. The problem is with error handling, that the syslog function that is implemented in libc and more or less standard is void. So the program never knows whether it failed. And even if it would know, it cannot do anything because it cannot log. So doing it in the program is the wrong place, and we do it in the kernel. We count it there, and then when we continue logging and the kernel tries to write to syslog again and again, and once it recognizes, oh, it works again, then it writes out a message to tell the user it didn't work. So it says send syslog, drop 2 messages, and it writes the error of the first failed send syslog. So I think that's inobuf or not connected, something like that. I think that's not connected. So if you log something before syslog-d is running, you get e not connected. So next thing, the timestamps. So as I said before, we take the local time in every change route because it's done by libc when the log message is generated. That's bad. And when you look at the format, we have no year, we have no time zone, we have no daylight saving time indication. So one time in a year, you see for one time every log message, there are double log messages, and then you have 1 hour gap half a year later. We have only second precision, no sub-second precision. And kernel, when the kernel is logging something, like the dmask buffer, the boot up messages, they don't have a timestamp anyway. So syslog has to do something for kernel messages. So what it's always doing for kernel messages is adding the timestamp. It looks at the message, says, oh, there's no timestamp, let's add one. And I extended that so that the timestamp is always optional. Syslog tries to parse it, and if there's no timestamps, yeah, then add one. That also corresponds to the way what is written in this Syslog RFC. Yeah, we also have devices that won't write timestamps, so Syslog has to be capable to add one if the device that we get the remote message from doesn't have a clock. And what I changed is that libc doesn't generate a timestamp anymore. So we always take the Syslog timestamp, and we have one central instance that is responsible for generating timestamps. New people coming to the talk? You just go in, find a place, and be quick. So Syslog-D generates the timestamp. It's one central instance. You don't have timestamps going back. It is a difference now. Before you logged when the message you did the timestamp in the program when the message happened. Now you do it in Syslog, so you have a delay there. And depending on when Syslog gets scheduled, it may be bigger or not bigger. So we can use higher precision. There's a new, so the solutions for all this is you can turn Syslog-D, you can give it the option -z, and then it generates in the new ISO format in UTC. That is the solution for we have no daylight saving time, no time zone, whatever. And there we have advantages. We can also use millisecond precision. So this format is in newer Syslog RFCs. And you see here you have the year, the month, the date, the hour, minute, second, and you have a precision. And this Z means it's Zulu time, so it's more or less UTC, GMT, whatever you call it. Here we are allow up to 6 digits precision or fractions of seconds, and you should. What's Henning saying there? That's correct. And what does our Syslog-D do? Yeah, I have to repeat it, sorry. So Henning says that UTC is without leap seconds and GMT is with, and we log in our systems without leap seconds. Thank you. You have the precision here. You are allowed to specify it by RFC up to 6 digits. I only do 3 because I did a measurement how long is the delay between logging in the program and reading it in Syslog-D, and I don't get a better precision, and that's roughly correct. And the RFC says by specifying the number of digits, you can say how precise you are. It's like physics. So we have other advantages by using send Syslog directly. So there are some situations where you don't want to call the libc functions. For you as application programmers, just use libc Syslog, it does everything for you. But we can do other things. We can call send Syslog from a signal handler. It's signal handler safe. We do have it in our libc when we see that memcopy does overlap. We have memmove. That's when you have memory regions that do overlap. And you have memcopy that is not allowed to use if the regions do overlap, because then it could do bad overwritings. And if a programmer does it wrong, then OpenBSD libc will generate a log message. But we don't want to call other libc functions from there, so we just did it for a raw send Syslog. Then we have the stack protector handler that sees that a stack cookie has been overwritten by buffer overflow. And in that case, you don't want to call other libc functions to to make it worse. Yeah, and it calls printf and does some formatting. So we do call some functions. We call some strulcat to create the message, but only that. And then we just call send syslog directly. So we get the message without doing more on this broken stack. And we also have some log message from the dynamic linker. It also cannot call libc because it's there to load libc. There we also use that. But don't do it. It's never necessary, except for those cases. So there are other places where we can lose log messages. We have the dmask, where the kernel prints the boot up messages and prints some debug messages if you enable device driver debugging. And basically it's a ring buffer, so kernel writes and syslog reads. It does a read on def klog, and it can overflow. And if syslog is reading slower than your device debugging messages appear, then it will overwrite and you lose some messages. And it's very hard. Once I tried to debug the USB stack and I thought, I have this message and have that message. And how can that happen? And I read the code and it couldn't happen. Yeah, but just an override. And those messages had nothing to do with each other. There were a lot of other messages in between. So the kernel is counting the bytes it is overwriting. It can count the bytes. And when syslog does a read and I see the counter is not 0 and I've lost some byte, then the first thing the kernel writes to the syslog is this message. And then you see, there was a gap. Now I know what's going on when I'm debugging this device driver. So what do we do when we log remotely? So syslogd can do a lot of things. So we have a sender, some log host that is sending us messages. We can get messages from some processes who do logging. The kernel generates its messages himself. And then we can write it to a file. We can spawn a process and pipe it into it. We have a memory buffer where we can store syslog messages temporarily. That's interesting for diskless machines. And then we have a special syslog-c command that communicates over a Unix domain socket with syslog. And then it reads out the messages. It has been added to OpenBSD. It was there when I looked into it, but it's an OpenBSD feature. Then you... Really? No. Yeah, but I think I saw it in other BSDs, so. So pipe is there in FreeBSD, so whoever copied it from whom. Okay, so Henning says everybody copies from OpenBSD, there's no other direction. But I doubt that that's right. And I would also say it's not good if it would be right, because there are also good other things in other BSD that we should share. So Henning, I'm supposed to repeat everything that Henning says, and now Henning did some jokes about himself. Okay. So we can send the messages to other remote logging facilities. We can write something to the console. We can write something to every user's terminal with write all. We can write something to special users. You can put users in your syslog file, so root gets messages, or Henning, or whatever. And you can write to special TTYs. So let's look at the details. That's more or less what I already explained. When you have the process, it uses either the new method send syslog or devlog. We kept the old method to be backwards compatible. Not everyone is using libc. There's a Perl module, syslog, where you can say, use Unix domain socket, then it uses that. Perhaps you have some programs around that still use that. And then you can add additional Unix sockets. That's basically for putting your devlog in all your change root environments. You can specify multiple of them on the command line. Say -a foo, -a bar. And then we have dev klog. That's for the messages generated by the kernel himself. So let's look at the remote logging. We have IPv4 and IPv6. When I started looking at Syslog, there was only IPv4. And we can do UDP, TCP, TLS on both sides. When I started, we only had UDP. So how does UDP logging look like? We have a single UDP packet, and that contains a log message. And that's it. Then we have some RFCs talking about the size. We have old RFCs that say, it should not more than 1,000. And then we have others who say, yeah, perhaps we should process 2,000. And then we have one RFC. If you don't make it longer than 1,180, the payload, then you can assume that it doesn't get fragmented, and if it doesn't get fragmented, then the chances are higher that it will reach the destination. So what I did is I took this value from one of the RFCs and truncate every message that I send to UDP to this length. So how does it look like? We have the priority we've seen before. We have the timestamp. Depending on how you set your syslog, with -z or not, you get the BSD timestamp or the ISO timestamp. So then the RFC says, here comes the host name. The RFC is called BSD syslog format, but our syslog doesn't have the host name. So I don't know which BSD syslog they refer to. We have an option, Marcus I think added it, where we can say -h to add this host name or IP address to every message. So and then there comes that what we receive from libc. It doesn't change. Yes. The question was whether I added at sending or receiving, and the answer is we add it when we send it. So what I do when we receive a message, we start parsing it. We are looking at the priority, there we filter it with our config file. We look at the timestamp, we add one if there is none. I've also added the -z option. If you find the old format, I replace it with a new format, because here you don't see anything if you have global logging. And then it also adds this when it does an UDP send. But that's also an OpenBSD extension. Another question? The question is what happens if the message is longer, and the answer is it gets truncated. I just cut it off. So how does it look in TCP? So there are a bunch of RFCs. We have the old syslog format, doesn't know anything about TCP. Then we have newer RFCs. They have one RFC about syslog in general. The next one is about syslog over UDP. Next one is about syslog over TLS, and there's no TCP. But then you have another RFC with a bigger, larger number, and there somebody has written down what he's found, what syslog implementation he has found that use TCP. So it's a collection of things that are out there, and usually it just works. So what we do in the TCP stream, we just put a new line to split the messages. And then there are other implementations that said, oh, we want new lines in our syslog messages, but that doesn't work if you write in the log file, because then you can't, because there, of course, the new line is the delimiter. And I replace every new line that I get somewhere with an underscore, by the way. So somebody also used null delimiter to split TCP messages. And then there are, so I split, when I read it, I think with new line and null. And then there's an octet counting format. That's the new shits. That's also in the TLS RFC. That says, you write a decimal number with a number of bytes, then you make a space, and then here are 60 bytes till here. And then the next message starts. So what I do when I send a message, I add a new line here. So I'm compatible with everything. except when somebody explicitly expects null delimiter, but I don't think that that is the case. So everybody splits that new line. It's just written in that RFC. And another advantage is when you put a new line here, it's much easier to parse those messages. If you just print them out, you get a new line every time you see a new message and just the octet count here in front. So TLS format, there we have an RFC, and it says octet counting is the only supported format. Then you must support 2000 bytes, and you should support 8100. And what I did is I added a global constant that says Syslog messages have that maximum size and everything else is truncated. So it's truncated in libc, it's truncated in the kernel, and it's truncated in Syslog. It can even truncate it multiple times because we are adding all those timestamps and changing things, and so it can get longer and then gets truncated again. So truncation is the right thing what to do with Syslog messages if they don't fit, because most of the time people can figure out what's going on at the beginning, and it's much better than dropping it. Don't drop them. So what I did also is converting Syslog to libevent. Before it had a poll loop, and doing all this TCP with multiple senders and multiple listeners and doing TLS is quite hard with poll. So Theo recommended to change to libTLS, libevent. That was the first thing I did. And then I linked to libTLS to do the TLS stuff. And I wrote a little wrapper that does encryption of libevent buffers by sending them through libTLS instead of doing plain read and writes. And this is one C file located in the Syslog directory, and it has already been copied to our LWD daemon that also needs that feature. And the thing is that in OpenBSD we have a rather old libTLS because we think the new one, libTLS2, is libevent. Libevent. The libevent is feature bloat, so we have a libevent of 1.14 something. Yeah, we are still API compatible. So the thing is that when you develop something with the OpenBSD libevent and copy it to Linux and take the old libevent there, then it still works. But I've done a lot of cleanup there, and internally it looks quite different. That's also the reason why I didn't add this feature to our libevent, because then we wouldn't be API compatible anymore. I've looked in libevent 2, they have something like that. So if you write portable programs, just use libevent 2, and if you do OpenBSD programming, just add it here locally. So what you also have to do when you do TLS, you have to care about identifying your communication partner and doing some certificate checks. And as usual, certificates are complicated. You have this public key infrastructure and nobody can set it up and understands how it should work and what it really does. So I've implemented everything, what you may need. And now I've put it on 4 slides for every use case. So what you always have to do if you want to accept encrypted messages, you have to provide a server certificate. So our syslogd uses a server certificate here, and you put it in etc SSL together with the host name you have. You can also put an IP address here. So the idea is to enable receiving TLS. It's not enabled by default. You put a T here, a minus capital T, and you say the host that's an IP address where you want to listen on. You can also say 0000 to listen on a star socket. You put a port. If you leave it out, the TLS port is 6514. We also have a 514 for UDP, and there's no well-known port for TCP because the 514 TCP number has been used by some remote shell, whatever, old Unix tool. But people use it anyway. Just uses, nobody does remote shell. And so what I did here, RelayD does the same. So you can put certificates for your machine and keys and private keys. You just put them there, and then Syslog uses it. You can also add the port here. Then you can use specific certificates for Syslog and RelayD. So why do we do that? Because when we have a certificate here, a server certificate here, the sender knows with whom it's talking. So the sender can identify the drain of all the messages, and that means the attacker cannot redirect the messages to himself, and he cannot see our messages. So another funny thing about TLS is you can have client certificates. So then the client provides a certificate, and we want to figure out whether it's the correct one. First, we have to enable it. Enable using TLS at all, and we specify a certificate authority file. And every time a sender tries to connect to us, we ask him, show me your client certificate, and we check whether it's signed with this CA, and if it is, we take the message, otherwise we don't take it. That means the Syslog can identify the sender who wants to talk to us, and the attacker cannot inject messages. So nobody else is allowed to send something to us. So that's the other side when we want to send something out. So the first thing I had to do is thinking about a format, how to specify that I want to use TLS. You have to give it in the config file of Syslog, syslog.conf, and what was there classically is that you use an @ sign, and then IP or host name, and then you send a UDP packet there. And what I wanted to do was able to specify, oh, take TCP, take IPv4, take IPv6. So you can say here TLS, TCP, or UDP, and then you can also optionally add in 4 or in 6, and then you will be forced to that protocol, to that IP version. And yeah, I thought about how to specify it, and then I took just something that looks like the prefix of a URL, because I'm sure that that will not collide with the host name, and I can parse it reliably. If somebody has a better idea and does things that doesn't look like, I'm open for suggestions. So then, if we want to send something out, the receiver syslog host, the receiver log host, has a server certificate, as every TLS server, and we want to validate it. So you can either specify a CA file, if it's your private PKA, or if you want to send something to well-known syslogds at the NSA or at Google or wherever you want to have your messages, then just take something that is provided by upstream. That's the default certificate store in OpenBSD. So Syslog must know the CA, and the host name must also be in the server certificate, so that nobody else that belongs to the same cryptographic infrastructure, like Comodo, can spoof it. And so the host name you specify here must be in the common name of the certificate, or in the subject alt name. libTLS handles that for us. And so we can identify to whom we are sending messages, and so the attacker cannot redirect it, and the messages are confidential. And if everything, this PKA and this thing is too complicated, it's turned on by default, you can just disable it. So for test environments, that might be useful, or if you don't care who's reading your messages and just want to get them off, use -v. So that's the final certificate slide. So here we use client certificates ourselves. You can specify them on the command line, and then the receiver can check them, and so he's sure that he's getting the messages from us, and the attacker does not inject anything. So how does the error handling work? We now I know what I wanted to say with that. We log all incoming connections. So what I first implemented is that we write a message every time we accept something and somebody closes the connection to us. And then somebody complained, oh, it fills up all our log files, so I converted that to debug messages. So Syslog is a special facility. So Syslog you can identify all the messages that are generated by Syslog itself. It's a facility, and I changed the priority or the severity to debug. And so it's not logged by default, but you can turn it on and see who is connecting to me. And when you set up your Syslog environment, it's maybe useful. And you can leave it on if you don't have too many messages. But if you have 1,000 clients rebooting every hour, then of course you don't want to see all that. We log connection errors. So when something goes wrong with a connection to a client, we log an error and you see, oh, something is wrong and I lost some messages or may lose some messages. We count the dropped messages. We have buffers to sending buffers for the messages. And if we get a sick hub, we throw them away. If we cannot write anymore, they fill up. We get a sick hub, we throw them away. We get a sick term, we throw them away. Then we count the messages that are in the buffer and log that. So you can see how many messages were not sent to a TCP destination. It's not completely reliable because the kernel also logs some messages, and the kernel throws the buffers away if there's an error on the TCP connection. But when you see, oh, we have a connection error, then you know, or there may also some log messages be lost because the kernel has thrown away the kernel buffers. And more than that are logged here. That are the messages that are dropped in userland, in Syslog userland. So it looks like this. Syslog-D, because Syslog generated the messages, dropped 2 messages, and it also logs the name of the host where it wanted to send them. And what I also implemented, when you have multiple messages, then Syslog-D writes message repeated. It doesn't write the same stuff all the time. It's important for local logging because otherwise you can fill up your log files easily. But it's bad for remote logging because when you have multiple syslogs, then you're not sure to which message the last message drop belongs. Then you can turn it off either for remote logging or even globally with the -R option. So now let's go to the conclusion. So I've the new message flow I have here, and I've made it italic, everything that has changed. So for the program, nothing has changed. The syslog call looks the same. And here in libc, we have no timestamp anymore. And we do a syscall, the special send syslog syscall, and not a send. The kernel has the send syslog, and it knows about logging errors and counts the errors. And Syslog-D still receives it. It's no difference whether we receive from a socket pair or from a Unix socket. It adds the timestamp. So we have one single instance responsible for timestamps. It writes it to a log file that didn't change. And it can also send to TLS or TCP. So that's new. So what also has to be done to be reliable logging, to have a reliable log system on your machine, first of all, Syslog may not die. Normally when you write programs, it's a good idea to die and fix the bug. If anything goes wrong, die. But if Syslog dies, you're blind. You don't see anything what's going on. Perhaps the attacker wanted to kill Syslog by some funky thing, and you don't know what's going on. So Syslog tries to run. It logs all the errors it gets at startup and whatever, and maybe you lose some log systems. You can't bind to the UDP socket and it doesn't work, or TCP socket is wrong, doesn't work. Gets a log message, but still running. Other messages appear. So we count the dropped messages internally. We make TCP and TLS support because they are more reliable and more confidential than UDP. We changed everything to lib event. That means we get safe signal handlers. We don't have to do all those dances with SIG proc mask to avoid some races here and there. All the signal handlers are not real signal handlers. They run the main program flow. Lib event handles that for us. We cope with file descriptor exhaustion. When you write a server that accepts a lot of things like incoming TLS syslog messages, you run against your process limit, and then critical file descriptors you cannot open anymore. For example, we run with privsep. That means we have file descriptor passing between a low privileged process that does all the network handling, because now we do TLS. We have to be careful here. And we have a privileged program that opens the log file. We have to do it at every SIG hub, for example, and we have to open consoles and TTYs and read user databases to send messages to special users. And then we do file descriptor passing. So we need a reserve of file descriptors. And Syslog handles that because incoming TCP and TLS connections will always leave about 10 file descriptors not allocated. They are for internal use. Then I already said we have privsep. What's important to avoid blind ROP attacks? There's an attack when you do fork, you have the same random address layout in two processes, and if you can probe the one, you can gather information about the other. And to fix that, you have to make an exec call. Normally, we exec the child. Here, we exec the parent, because it was much easier to implement in Syslog-D. Because Syslog-D does a lot of startup things, and then it does the fork. And so if I exec the child, all the startup is lost, and the child needs the startup. Initialization. And the parent only serves some requests like do DNS, open some log files, and there it's better to lose all the state. So I do the exec, and I have just a minimal program just doing the iMessage requests with easy things, and we run pledge in both processes, the child and the parent. So I've already written some tests. Usually before I change programs, I write some regression tests, and then I fix the bugs, and then I add the new features. That's the evil thing about writing tests. You always find bugs, and then you have to fix them. So don't do that. So the tests work in the way that they generate some config, start the Syslog-D, then they have a client and a server process. The client process generates some log files, then I stop everything, and then I check. And what can I check? I can check the standard error output of Syslog-D. Syslog-D runs in debug mode, where every debug message and all other log messages are printed there, so I can see what's going on. The client writes a log, but it's sending to Syslog. It can use native send Syslog methods, or UDP, or TLS, or TCP, or whatever. The server also has a log, what it received from Syslog-D. We have a log file. We can look into that. I spawn some pipes there, and I look into that. I make some console redirection to see that everything goes to the console that is specified there. I create some fake users and that I enter in the var user temp file, and then Syslog-D looks into that and writes it there on the console, and I've redirected the console and look into the user's console, or the user's terminal, sorry, it's a terminal redirection, and I look into the terminal that from my fake user. Syslog-D creates a k-trace. I can grab in the k-trace if it does the correct system calls, and I can look in the fstat if it has opened the right sockets. Yes, a question? Oh, that's not the regression framework itself. It's the question repeating. The question was how I test that something has been written to the console with our regression framework. And the answer is it's not the framework itself. It's something implemented in this Syslog test. It's some Perl modules that do things. And there's the thing that you have in X. You have the X console. It's a program. And it tells the kernel redirect everything that's written to the console into this window. And I use that mechanism to log everything that is written to the console into a process, and the process writes into the file, and at the end of the test, I grab in the file. Yeah. So, and of course, software is never finished. I always say only dead projects generate stable software. So what else can we do here? So the thing is, when you prepare such a talk, you look into the code and think, oh, that's all buggy. That could be done better. So the first thing I thought is all those initialization errors that are written to standard error or the console when syslog goes up cannot be written into a log file because they are not there. And I could count the errors. I have a diff for that. It's on tech. And that's meant as a hint for some co-developers to do the review. Then I went to our quality assurance guy at Genua and said, oh, now we have reliable logging and we don't lose anything. And he tested it and says, oh, when the file system is full, you stop logging. Yeah, and it's true if syslog gets twice an error when it writes to file descriptor and its file system exhausted, then it stops logging there, even if the file system gets empty again. So I have a diff for that, but it is on top on the other diff, so I will send it out when the first one has been reviewed and committed. Also have a test for that. I create a file system with def vnd, fill it up, write a log file to that, get the error, and then check that and I empty it again and check that it's logged again and read all the debug messages that syslogd creates for that. So then I have read the old RFC with the host name, and there's a new RFC, how to write remote syslog messages, and they have version numbers there and other features, and we are somewhere in between, but not quite, and perhaps we should get more RFC compliant. That's also when I was preparing the talk. And then, yeah, you go through these conferences, talk to other developers, they say, oh, I do a talk here, make some promotion that people come here. And then MPI says, oh, I still have a bug there, and can you fix it before you do your talk? No, didn't fix it, but I promised him to put it on the slide. And then yesterday at the social event, I was talking with Imre from the Dragonfly project, and he said, oh yeah, you know when you do this startup, then you get the DMAS things, and when syslog reads the DMAS buffer, it adds a timestamp there. And wouldn't it be better when the kernel adds the timestamp? It could use the uptime, and syslog can create it to regular timestamps. Then we would know in which order those messages come. And so the problem is in our company, we have a central configuration thing, and they put every log message in a database, and then they sort by timestamp. And all those messages coming from the kernel have the same timestamp, because when they were read, and then they log it, show it randomly to the user. That's a bad thing to do. And the idea was, if the kernel would log it, we would see when the DMAS messages appear, we can see where were the delays, how long did it take. That's one thing. And then I thought about it, when we would do that also for the send syslog call, we would get the time when the program does the log, and not when syslogd gets scheduled and reads the log, and we could get more precision. So I'll think about that if I want to implement it. Yeah, and that's it.
So it turns out you have already talked about my first of my notes about bin uptime in the kernel and kernel timestamps, but I have another one. You said you're opening a socket pair and you're marking a socket as used by syslog by this special ioctl, right?
Yes.
So there is a race condition if you do that, and then some program tries to represent itself as a syslog daemon, and then it waits until the syslogd gets sick up, when it closes everything and tries to reopen again. In this,
you do the ioctl on the dev klog file descriptor.
Yeah.
So you have to open dev klog, and
yeah.
depending on your permissions in /dev, only root can do that.
Okay. Yeah. So you have to check for root, and you have to check to be not rooted in this case, right?
Yeah, because there's no device.
Yeah.
Otherwise.
Okay.
So you need access to devklog to be a syslog, a reader for Syslog.
Yeah, and if you are root, you are fucked up anyway. So
yeah.
Like, for a game.
Okay. More questions?
For your new syscall, why are you using a void pointer? Is there a valid use case where it's not a character pointer actually?
Well, that's Theo's idea.
Okay, so I have to ask him the question because if it's only because it's like write and read, that's stupid. There's no valid use case for this not to be a character. This is not systemd after all.
Yeah. So there are two possibilities. Either Theo has a good reason for it, or it was just too stupid to copy it correctly from the main page.
Okay, fair enough.
Yes.
I'm curious, what's the motivation for using the additional socket pair instead of reading and writing directly from the klog for the Syslog messages?
So in klog, you have the real kernel messages. They have a different format. They are different from user messages. So you want to have a difference. The klog buffer is more or less the thing that is in dmask. So if you call the log function in the kernel, it gets added to the dmask, and it can be read by syslogd from devklog. That's very distinct from userland logging. So we added the new syslog, the syscall send syslog, and their new mechanism was needed, and Theo did it with a socket pair, and I think it's a good idea. So, but I don't know exactly why this approach was chosen.
Any more questions? Then let's thank Alexander for his great presentation.
Thank you.